What characteristics would you expect in the hysteresis loop of a ferromagnetic particle with average magnetocrystalline anisotropy, which is so small that it consists of a single domain? Suggest an application. So we're looking at the switching or magnetization reversal of a single domain ferromagnetic particle. So where will this single domain point? The magnetization in the single domain has to point along the easy axis. So single domain magnetization points along the easy axis, as we have seen in the previous problem. Now that easy axis can be due to shape anisotropy. So it can be dictated by shape anisotropy and magnetocrystalline anisotropy. All right. And in the reversal process, we don't have any domain walls present in this system, so it will not involve any domain wall motion. Since there are no domains, magnetization reversal does not involve domain wall motion. Okay, so we will have the rotation of the single domain magnetization. So we can only have two scenarios, reversible or irreversible rotation. Okay, so when do we have reversible rotation? When do we have irreversible rotation? So when we apply the magnetic field parallel to the easy axis opposing the direction of magnetization. So this is opposite to magnetization. This will lead to switching at the coercive field, which is equal to the anisotropy field, 2k anisotropy constant divided by the saturation magnetization ms, that is uniaxial anisotropy case. And we're going to end up with this square hysteresis. So it's going to switch between two directions, let's say minus x and plus x direction, and the switching will occur at plus hc and minus hc, the coercive field, which is the anisotropy field. So this is basically our Stoner-Wolfart type switching. We're going to have square hysteresis, which is due to irreversible rotation. So you can see that we have non-volatility. If we remove the field after the magnetization switching occurs, we go to a different state. So it's not the state we started with. So we start with minus saturation magnetization and we switch, we go to plus saturation magnetization, remove the field. We don't go back to minus ms, we have plus ms. So this is minus ms plus ms, and it is irreversible. Okay, so When do we have reversible rotation of magnetization? If the magnetic field is applied along the hard axis, if H points along the hard axis, there will be no hysteresis and we will have reversible rotation. It's the coherent rotation of the magnetic moments. As soon as you remove the magnetic field, the anisotropy will dictate the magnetization direction. So if you start with zero magnetization here, you apply a field in the hard axis direction, you will see that it will saturate in the hard axis, but when you remove the field, it's going to go back to its previous state, which is dictated by the anisotropy. So the magnetization perpendicular to the easy axis will become zero because it will be pointing in the direction of the easy axis. And what is the application of these single domain particles? Basically, this is these domains form bits in our magnetic recording. For example, hard disk drives. So they are representing these two magnetization orientations will represent 0 and 1 states of the bits for binary logic. Okay, so we have looked at a single domain ferromagnetic particle with average magnetocrystalline anisotropy. The orientation of the domain is dictated by the anisotropy of the system. It's shape anisotropy and magnetocrystalline anisotropy that can contribute. And we don't have any domain, so there is no domain wall motion in the magnetization reversal process. If we apply a magnetic field parallel to the easy axis, we get a square hysteresis loop with irreversible rotation of the domain because these two states are both minima in the energy of the anisotropy. So anisotropy energy is minimized in both cases, so it's irreversible. However, if you apply a magnetic field along the hard axis, you're going to slowly rotate the magnetization towards the hard axis. That's a reversible rotation because when you remove the magnetic field, the magnetization along the hard axis will become zero. The magnetization will again point along an easy axis, which is dictated by the anisotropy. The application of this is magnetic recording.